All right, so in this video, we're going to continue where we left off. We're going to talk about variance. The variance of a random variable is the expected value of squared deviation from the random variable's expected value, so the mean of the expected value. So I'll write that out. So the variance, the notation for this will be var variance of x. So the variance of our random variable is going to be equal to the expected value of our random variable minus the mean, so squared deviations of the mean. And so one question you may have is why squared? Why not absolute value? So with the squared, we can weight the ones a little bit further away, a little bit more, and it's linear. If we just did the absolute value, if we did the absolute value, this isn't linear. And that we'll talk about that later on in the class as to why that's important. If you took a maybe a higher level stats class or econometrics, this is something that they would talk about, spend some more time on. But again, we're not going to really do any proofs in this class. It's not what this class is about. All right, so it's the expected value of the squared deviations of the mean. And it's also be another way to notate this is sigma squared. So this is sigma squared. Let's put an X down here so we know it's for the random variable x. Another thing to remember is the standard deviation. So let's say standard deviation of x. This is equal to the square root of the variance of x. So this would be equal to the square root of the variance of x, which would just be sigma x. So whenever we talk about our data, whenever we talk about different things, we typically refer back more to the standard deviation than the variance. That's because for the variance is in terms of units squared. So say you're looking at the time that someone spends in your store. If our data that we're analyzing is time customers spend in store, say spent in store or maybe on the website, the variance of this would be in terms of units squared. So that's kind of hard to visualize. But the standard deviation would be in units of just time spent in the store. So that's a little bit easier to visualize. Now remember, so if we're going to write this out, let's write it out with the formula from before. So the variance of x would be equal to, remember, the expected values are probability weighted. So we're going to probability weighted square deviations of the mean. So this would be x1 minus the mean squared multiplied by the probability of x1 because it's probability weighted. And this goes all the way to xn. So xn minus the mean squared multiplied by the probability of xn. And this could be written with the sigma notation like before. So from xi or I to I equal 1 to n, you would get probability of xi multiplied by xi minus the mean squared. When taking the variance of something with a constant, let's say we want the variance of ax. Maybe this is maybe x could be portfolio returns or something like that. Maybe a weight, whatever it is. Just like before, this would be the same as the expected value of ax minus a mean squared. And then when something squared, it's multiplied by itself twice. So this would be the same as the expected value of ax minus a mean multiplied by the ax minus a mean. It's the expected value of this. And you can factor out the a. When you factor it out twice, which would give you a squared multiplied by the variance of x. So this is important. So if you have a constant multiplied by a random variable and you're trying to take the variance of it, it would be the same. You factor it out, you get the constant squared multiplied by the variance of that random variable. And then An example of this would, let's do another portfolio. Let's do another portfolio return. Let's say RP. Let's do another 2-asset portfolio. And this should be a little bit of review for you. So let's say return of our portfolio is equal to weight 1 of asset 1, to return the weight of our first asset multiplied by the return of our first asset, where return is a random variable and the weight is a constant, plus weight 2 times R2, where again, weight 2 is a constant and R2 is a random variable, the return of that second asset. So if we want the variance, of our portfolio return, this will mean we want the variance of weight 1 times return 1 plus weight 2 times return 2. Again, where this would be the first asset, this would be the second asset. Just like before, whenever we do this, we can say this would be equal to the variance of weight 1 times R1. But whenever you do this, for every pair of random variables, you're going to have a covariance term. So this would be variance of weight 1 times R from return 1 plus the covariance of weight 1 times return 1 and weight 2 times return 2, plus the variance of return 2 and of weight 2 times return 2, plus, remember, we have another pair. This time it's return 2 and return 1, plus the covariance of weight 2, return 2, and the other asset, return first asset. So now the covariance of R1 and R2 is the exact same as the variance or covariance of R2 and R1. These are exactly the same. So let's take another step further. This would mean we get the variance of weight 1 times R1 plus the variance of weight 2 times R2 plus 2 times the covariance of weight 1 times R1 and weight 2 times R2. Put a little comma in there. You may remember back in your stats class, I'm going to make some room up here so I can write it out. So back in your stats class that you would have taken at some point, the covariance would be the product of the difference of our first random variable from the mean, difference between that and the mean multiplied by the difference of the other one. So let's write that out. So covariance between let's write it all out. Or let's do a basic example. So just two random variables, x and y. This would be the same as the expected value of x minus the mean of x multiplied by y minus the mean of y. We can apply this to down here, this term. The covariance between weight 1 times R1 and weight 2 times R2. Again, where weights, their W's are constants and R's are our returns. This would be the same as the expected value of W1 times return 1, or weight 1, minus W1 and our average. Let's do R1 bar. Our expected value, or our mean, return 1 multiplied by return 2, or weight 2 times return 2 minus weight 2, and our average return for a second asset. You can factor it out. You can factor out the W1 and you can factor out W2, which would give you, and it's not like variance. We're only factoring out once here. So we factor out W1, weight 1, and we can take it out here. And we can factor out W2, and that would also go out front. So weight 1 times weight 2 times the covariance between return 1 and return 2. So now we can plug that in down here, and we can simplify this a little bit more. So now this from before, if we can factor out weight 1, and that becomes weight 1 squared multiplied by the variance of our first asset's returns, plus we can factor out weight 2. That becomes weight 2 squared multiplied by the variance of our second asset's return, plus 2 times weight 1. Remember, this is from up here, times weight 2 times the covariance between our first and second return. And you can take this further, and instead of doing a 2-asset portfolio, you could do an nth asset. So it could be a 50-asset or 100-asset portfolio. I have notes on the PDF, but it's a little bit beyond the scope of this class. I just wanted to give you an example of how this would apply to a real life scenario, besides just some of the stuff we do with later on in the class. So this sums up the math portion of 4.2. In the next video, we will apply some of this in Python.